everyone. So this week, our last type of comparison we're going to do is application problems. So, the first week of review was comparing graphs of linear, exponential, and quadratic functions. Last week was comparing tables of linear, quadratic, exponential functions. So this week and next week, we're going to talk about application problems for linear, exponential, and quadratics. But because we hadn't done quadratic application problems as part of the quadratics unit, because this whole distance learning thing, I'm going to save quadratic application problems for next week. So this week, all we're doing is linear and exponential applications and comparisons. And so the point of comparing application problems is hopefully, by now, you guys have a solid foundation of linear, exponential, and quadratic functions. And now you can use them in practical applications. So comparing when would you use a linear function versus an exponential function versus a quadratic in the real world. And I always try to make sure that everything that I teach you guys comes back to a real application and real world point of view. So at the end of the year, the last thing we talk about is comparing application problems. So we're only going to do 2 this week, and then we'll do the last one next week, and that'll be our year. So a linear example. An Uber ride in Portland costs $1.10 per mile with an additional flat fee of $5 for the ride. So write an equation to model this situation. X represents miles, and Y represents total cost. So remember, when you're writing a function that's linear, you have to fill in 2 pieces. You have to find the slope, and you have to find the y-intercept. But in application problems, the slope is your rate, and your y-intercept, so if you think about, we talked about this once upon a time, a y-intercept, so if my line looks like this, for example, a y-intercept is, typically in application problems, this would be like 0, 4, for example, The y-axis represents the amount of something, and the x-axis represents time. And so when time is 0, that's your, the y output is your starting amount or initial condition. So your b value, your y-intercept, is really your starting amount. Because even though the line goes backwards in the negatives, we can model that if we went back in time, what something would look like. Because over here, remember, is like this would be like the negative time section. This is positive time. So typically we only care about looking forward into positive time, but at 0, this would be your initial amount of whatever. And so this is just a general discussion about what a linear model looks like. So to write an equation, you have to find your slope, which is represented by your rate of something. And so your rate is usually something per something. So it's like something per something, because your slope is your change in y over change in x. And so for this example, it's cost over time. So if we were going to graph this, your y-axis represents the cost. My handwriting's so messy today. The y-axis represents cost, output, and the x-axis represents the number of miles. So as you go a certain number of miles, the cost is going to increase. Well, for this one, when you get in the Uber, there's a flat fee of $5. And so no matter what, the initial cost is going to be at least $5. And then as you ride, it's going to go up from there. So your B value in this case is 5, because that's the initial cost no matter what. And then your slope, it is $1.10 per, so up here it says $1.10 per mile. So that's per 1 mile. And so your slope is $1.10 over 1 mile. And so the reason why your slope is the rate that's given is because your slope, it's rise over run, right? So the rise would be the dollar amount and the run would be the number of miles. So the rise is dollar amount, the run is miles. And so that's why it's change in y over change in x. So it's dollar amount over miles. And so for 1 unit, your slope is 110 over 1. So your m value is just 1.10. So your equation would be y equals, I'll use the 1.10x plus 5. So it's your rate x plus the initial amount. So it's $5 just to hop in the Uber because there's that initial fee. And then it's $1.10 per mile. And so then x represents the number of miles that you go. And so part B of the question says, well, what would the cost be of a 5.5 mile Uber ride? Well, y equals 1.10 and then plug in 5.5 plus 5. So because we went 5.5 miles, so grab a calculator, 1.10 times 5.5. So it's $6.05 just for the rate, but we have to add 5 for that initial fee. So if we went 5.5 miles, it would be $11.05. So y equals 11.05. So if you want to put dollar sign up front. So it costs us $11.05. So we did a bunch of linear applications once upon a time. It's been a little while. We've also done some exponential applications, but again, it's been a little while. So remember, exponentials are represented by, there's growth or decay. I'm going to draw a line. We could have a function that starts near 0 and gets really big. So we've got growth. We've also got decay. And again, your y-intercept, one more time, represents your starting value because, you know, your x-axis is usually some kind of time-dependent thing, and your y-axis is the amount of something. And so your y-intercept is going to be 0, some number, and this number represents your initial amount. And typically, you know, in exponentials, we talk about populations or money, and so that's what we're going to stick to. So a home was purchased in Washougal for $415,000, and it grows 3% in value every year. So we know it's a growth function. Our starting amount is $415,000. So first up, write an exponential equation to model situation. X represents years, so X, like I said, is usually time. Y represents the value of the home, so the amount of money it's worth. But if you recall, this was the, so a typical exponential is y equals a times b to the x. But when we are given a percent, we actually have to do a little bit of work to find that b value. It's not just given to us. And so that's where this comes in. So r represents your percent as a decimal. So we have to take that extra step of turning your percent into a decimal and doing 1 plus that, or 1 minus that, depending on if it's growth or decay. So you do 1 plus r for growth. You do 1 minus r for decay. Because if you do 1 plus a decimal, it's going to be greater than 1, so it's growing. If you do 1 minus some decimal, it'll be smaller than 1, so it's decaying. So in this case, r is, if it's 3%, that's 0.03. Don't forget it's 0.3. If it was 0.3, that'd be 30%. So to write our equation, we also need the a value. And remember, your a value is your y-intercept, which is the same thing as your starting amount. Starting amount. So your a value is $415,000. So our equation is y equals $415,000 times 1 plus 0.03 to the x. And then I usually take this step real quick. 415,000. I do 1 plus 0.03 is just 1.03 to the x. And so that's your b value. So that's your multiplier. So this is our equation, and then they want to know what's the value of the home 11 years from now. So we'll plug 11 in for x. So y equals 415,000 times 1.03 to the 11. All right. And so then just go to your calculator. I would recommend using Desmo Scientific. I just have my calculator with me, and just type the whole thing in, 415,000, parentheses, 1.03, and then raise it up to the 11. So remember, put 11 as the exponent, hit enter. And we got, it's worth $574,457. You don't have to, don't worry about the decimal. Just round to the nearest whole number. 574,457. So that's how much money it's worth in 11 years if it grew by 3% every year, which I feel like that's pretty reasonable. All right, so here's an example of linear, here's an example of exponential. Now, they won't be labeled for you guys. So here's a couple examples. A tech company startup in San Jose began with $850,000 in investments and is losing 9% of their funds every month. All right, well, is this going to be linear or exponential? Well, if they're losing a percent, that means that this is going to be an exponential model. This one's exponential because we're losing a percent. And the percent ones are going to be the a times 1 plus or minus r to the x, because r represents your percent as a decimal. Also, if it's losing a percent of its funds continually, that means it's going to be growing or decaying exponentially. But it's not saying that there's a rate, right? There's no rate given. No rate given. They're not saying it's like $10 per month. They're saying it's 9% of the current value per month. And so this is an exponential. So write an equation to model where x is months, y is the amount of money. So we have to write an exponential. So the base function is y equals a times 1 plus or minus r to the x. So then we have to ask ourselves, first of all, is it going to be 1 plus r or 1 minus r? Well, it's losing 9%. So if it's losing, that represents decay. And so if it's decaying, we'll do a times 1 minus r to the x. So then our a value, their starting amount was $850,000. So a is 850,000. And then r, if it's 9%, r, your decimal is 0.09. So our function would be y equals $850,000 times 1 minus 0.09 to the x. And I'm going to clean this up a little bit. I'm going to do 1 minus 0.09 is 0.91. So y equals 850,000 times 0.91 to the x. So that's our equation. Then part C, how much money does the company have in 8 months? Well, let's plug in 8 and see how much money they have left after 8 months. 0.91 to the 8. So then just go to your calculator, type the whole thing in, 850,000 times 0.91 to the 8. So they only have about $400,000 left, so that's not a good time. So after 8 months, they have $399,714 left. So just under $400,000. So they're losing money pretty quick. All right, our last example. Little Smitty is working on getting healthy after noticing his weight was 240 pounds, which remember, he's little. He's only, he's like 5'6" or something. There's a quadratic application where we find his heights. I'll have to find that one for you guys next week. So he's trying to lose some weight. He is able to lose 2.5 pounds per month. So here's your rate in his weight loss quest. So this is a good indication that it's linear because it's a certain amount per month. So we're losing the same amount per something. So this is linear because rate is given and something per something. So let's write a linear equation. Y equals mx plus b. So we need to find the slope, which is our rate, and the b value, which is your y-intercept, but in this case, remember, it's your starting amount. So, remember, he should be losing weight. So, little Smitty has some starting weight here at 240. And it should be going down continually because he's trying to lose weight. So, your slope should be negative. So, your M value should be negative. So, our M value, he's losing 2.5 pounds per month. So, he's losing 2.5. So, it's negative 2.5 is your slope. And then your B value, his initial amount was 240 pounds. So, your equation is y equals negative 2.5x plus 240. So then how much will Smitty weigh 1 year from now? So this one's tricky. So if you want to know how much he weighs 1 year from now, remember it's in pounds per month. So what are we going to plug in? Well, a year is 12 months. So y equals negative 2.5 times 12 plus 240. Let's see. Negative 2.5 times 12 plus 240. So after a year, he weighs 210 pounds. All right, guys, so these should be your review problems. And so, like I said, your quiz is just going to be, you know, these are level 3 type questions. The level 2 questions are going to be identifying pieces like we did throughout. And let me know if you guys have any questions.